The even function property applied to double integrals is the subject and theme for this video. I am Mr. Ish. Thank you for joining me. We know the even function property is very applicable to integrals in terms of a handy and useful property. In terms of single integrals, a good representation could be like this. For an even function, this right here is f of x. You would have to have a y-axis symmetry with symmetrical limits minus a to a. The area over here, in terms of single integrals, you can represent it as minus a to a f of x dx would be equal to a shorter, more handier version of this integral from 0 to a. You're evaluating it, multiplying by 2 f of x dx. You've seen this, and this right here is a property which is applicable and represented in terms of single integrals. Rather than doing area from minus a to a, you do 0 to a and you multiply this by 2. Now doing the exact same representation with double integrals, it's gonna be similar and easy. You have minus a to a, this is the area you're looking at. You can also do a 0, and we can pretend this upper limit here is a c. How would you write this in terms of double integrals? You can. I'm going to do an initial integral dx with respect to dy. I'll be doing ideally from minus a to a, but look, these lower and upper limits are tracking the curve. I need to bring in the effect of that movement and that tracking, and I can. Since I'm going to do eventually with respect to dy, rather than looking at f of x, which would be like a y equals equation, I need to be looking at f of y, which is synonymous to x equals equation. So I can do f of y here as my upper limit, and I can do minus f of y as my lower limit. These are with respect to dx. This is like me saying minus a to a f of x dx. This is like what you're seeing here. Eventually now with respect to dy, 0 to c dy. Everything you're seeing right over here is equivalent to this. This is the double integral version, that's a single integral version. Now let's represent this in terms of double integrals. I would be looking here from 0 to a. In this part right here, I would multiply it by 2. I can have this lower limit go straight up, no modification, that would be 0. My upper limit will track along the curve, that would be f of y. Remember, everything is eventually with respect to dy, hence the equation is x equals format, f of y. I have a 2 over here which I can bring, and then I'm looking 0 to c. Because I'm doing eventually with respect to dy, I need to be looking at lower and upper limits in terms of y-axis, 0 to c dy. What you see over here, this part right here is equivalent to this part right here. This is a double integral version, that's a single integral version. You can easily compute this. I'll only compute this one side, the other side is exactly the same because this 2 can be pushed out right here. From here the antiderivative is x, you're doing f of y and minus f of y. You will be doing upper limit minus the lower limit, f of y minus f of y will be 2f of y. This 2f of y will now become the integrand of your dy integral, and you'll push the 2 out. You'll have a 0 to c f of y dy. You can do the antiderivative in terms of a capital letter f with the upper limit c minus capital F with the lower limit is 0, and this would represent the end result from here, the left hand side and the right hand side. I'm just not showing you this side because it's exactly the same. Just don't always assume here that f of 0, the antiderivative with the 0 value coming in, is equal to 0. In some cases it is, in some cases it isn't. We're just looking here at the expression and result. The left hand, right hand expressions will be exactly identical. This right here is the even function in terms of single integrals. The lower expressions here are the even function property with regards to double integrals. Have a good day. Thank you.